Hey guys, we're going to look at Lewis dot structures for today. Tomorrow we're going to look at VSEPR, valence shell electron pair repulsion, and that's going to require you to be able to draw Lewis dot structures fairly competently. So I want to make sure you guys know how to do this. Some of you should have already seen this in your first chemistry class, but some of you it may have been a while. So I want to make sure we go through this pretty slowly so that you guys are pretty thoroughly, I guess, so you guys have a good idea of what we're doing. First off, Lewis dot structures are kind of these weird structures down here that we see with the lines and the dots and the elements. What we're basically doing is showing the arrangement of all the atoms within a molecule and showing all the electrons and how those are arranged as well. A couple rules we need to keep in mind. First off, we're trying to satisfy the octet for each atom in the compound. There are some exceptions to the octet rule, and we'll talk about those in just a little bit. Okay. The next thing is we're only showing the valence electrons within the compounds, nothing else, nothing more. So we'll have to count out the total number of valence electrons and then satisfy the octet rule with only those. We cannot add extra electrons or take away electrons that are there. So keep that in mind. Okay. A couple terms we need to keep in mind. First and foremost, central atom. When I refer to the central atom, I'm referring to the atom that goes in the center of the Lewis dot structure. What that means is you will have to identify which atom goes in the center when you're drawing them. Everything else is called the outer electron. Now, some of you that have taken AP Bio before have seen some of the complex structures with all the carbons and the different functional groups off of it and all that fun nonsense. Okay, well, each of these carbons would represent a different central atom, and we would label them as carbon X, carbon Y, carbon Z. And I would say, what is the structure around carbon Y? And you'll be able to tell me that after a little while. So each one of these is technically its own central atom of its own structure, even though they're all part of the same structure. And we can talk a little bit more about that later. Right now, that's not important. We're going to focus on the simple ones. A couple more words. Single bond is a straight line representing 2 electrons. Double bond is 2 lines representing 4 electrons, 2 each, and a triple bond is 3 lines representing 6 electrons, again 2 each. We also have what's called a bonded pair, which is any bond, and then if we have any lone electrons like this, let's say we had carbon with 2 lone electrons on it and bonds off of it, okay, this would be called a lone pair. So we have bonded pairs, meaning they're lines, lone pairs, meaning they are unbonded and just the dots. Okay, some rules we need to keep in mind. First and foremost, our job here is to tally up the total number of valence electrons within the molecule. Once we have the total number of valence electrons, we'll determine the central atom. Your central atom is typically the first element in the compound, which is typically the closest to the left side. So if we were to look at CH4, carbon is our central atom. Now, hydrogen can't be our central atom because it can only make 1 bond here. But carbon would be our central atom in this case. Let's say we have H3N. Hydrogen's our first element. Carbon's first element here, so it's very obviously our central atom, but hydrogen here is our first element. It can't be. So nitrogen, again, would be our central atom. So in most cases, the first element will be our central atom. Sometimes we may have to go to the second one if the first element is hydrogen. Okay? From there, we'll draw the central atom, and we'll draw single bonds between all the atoms around the central atom. Okay, remember each bond represents 2 electrons. So you'll count up how many electrons you've shown, and then draw the remaining pairs, or draw the remaining unpaired electrons around the outer atoms first, and any extras will go on the inner atom, or the central atom. Once we have all that done, we'll see if everything obeys the octet rule. If it doesn't, then we'll make doubles and triple bonds as needed. And we do have some exceptions, so let's look at some of our exceptions here. Okay. First and foremost, hydrogen is one of our big exceptions that we'll see a lot. It will only hold 2 electrons, which means only a single bond. That's one reason it cannot be a central atom. It can only hold 1 bond. Holding 1 bond can't be central. Okay, boron can hold up to 3 pairs or 6 electrons. It does not hold the customary 8 of the octet rule. Okay, beryllium is also a similar one. It only holds 4 electrons or 2 pairs. Okay, and then we have this rule that allows for us to hold more than 8. Hydrogen and boron and beryllium are less than 8. Then we have this rule that gives us more than 8, and it's anything that has access to the D shell. Well, remember the D shell comes in on the 3rd period. Remember, scandium to zinc is 3D. So anything on that 3rd period and below has a D shell it has access to. So this would include aluminum, silicon, phosphorus, sulfur, chlorine, and argon. They can bond, and they can have more than 8 valence electrons. Now keep in mind that doesn't mean that we're trying to get them to have more than 8. We're still trying to get them to obey the octet. It just means that they may hold more than 8 if they have to. Okay, so let's look at some examples. Let's say we are looking at CH4. We've looked at that one a little bit earlier. First thing we're going to do is add up our total number of valence electrons. Well, carbon has 4 valence electrons. Hydrogen has one valence electron, and we have 4 of them. So what that means is we have 4 coming from carbon and 4 coming from hydrogen, giving us a total of 8 valence electrons we have to show in our structure. So carbon is our central atom. We draw our single bonds to the hydrogens, and we typically do 1 on each side, kind of like the box we did with the Lewis dot structures of the atoms. And then from there, we count up how many valence electrons we have shown. Well, each bond represents 2. So 2, 4, 6, and 8. So we've shown all 8 of our valence electrons. So the next thing is to see if everything is satisfied by the octet rule. Hydrogen only wants 2. So 2, 2, 2, and 2. Carbon wants 8, and this bond is being shared equally between them. So 2, 4, 6, and 8 are going to carbon. So all elements are satisfied, and we're showing all 8 valence electrons. So this one's good. Let's look at another one. Let's say we have NCl5. Not 5, I'm sorry, 3. We'll look at Cl5 in a little bit. 3. Okay, nitrogen has 5 valence electrons. Chlorine has 7, and we have 3 of them. So this is 21 coming from chlorine, plus 5 gives us a total of 26 valence electrons. So we draw what we have. Nitrogen's our central atom because it's the first, and it's the farthest left. Then we have our chlorines around it. Okay, and that gives us 2, 4, 6 electrons shown. That means we have 20 more. So 2, 4, 6, 8, 10, 12, 14, 16, and 18. Okay, so that means we have 2 more to show. We have basically right here 24, 2, 4, 6, 8 on all of them, 24. We have 2 more. The chlorines are satisfied, they have the octet, but if we look at nitrogen, 2, 4, 6, it needs 2 more. So we throw those 2 down here, and that gives 8 for the nitrogen and 8 for each chlorine. So that means everybody's satisfied, and we've shown all 26. And you'll notice I'm making my dots kind of big and taking my time to write them. That's because if you were just kind of writing quickly, sometimes it's hard to tell if something's a line or if something's a dot, or if maybe you just dropped your pencil and made a mark somewhere. So make sure you are being very definitive about your dots so I know for sure whether you mean a dot there or whether it's an accident. Okay, so let's look at another one. Let's say we have CO2. Okay, well, carbon has 4 valence electrons, oxygen has 6, and we have 2 of them. So this gives us 12 plus 4, 16 total valence electrons. So we have carbon in the central atom because it's the first one and the farthest left. Okay, and we have our single bonds to the oxygen. So that gives us 2 and 4. That gives us 12 more to show. So 2, 4, 6, 8, 10, and 12. And something to keep in mind, it doesn't matter where you draw these oxygens around the carbon. They can be at 90-degree angles from each other. I'm just drawing them out like this because I like everything symmetrical. Okay, so this is 2, 4, 6, 8, 2, 4, 6, 8. All 16 are shown, which is a problem because check out carbon. Carbon only has 4 electrons around it right now. It wants to have 8. I can't just draw random electrons in here. I can only use the 16 I have shown, which means our last rule is what comes into play here. Carbon is not being satisfied by the octet rule, so we have to make it satisfied by grabbing other electrons and making double bonds. So I'm going to come out to one of the oxygens and steal 2 electrons from it and move it between the 2. So this oxygen still is sharing those 2 electrons, but now carbon has access to those 2 electrons as well. Now that gives me 6 around carbon, 8 around this oxygen still. So I'm going to come to this oxygen, steal 2 more, and put them on this side. So now that gives me 8 around this oxygen, 8 around carbon, and 8 around this oxygen. So now I'm showing my 16 valence electrons, and everybody is sharing 8 valence electrons equally, so everybody is satisfied. Let's look at a polyatomic ion real quick. Let's say we have NO3, -1, nitrate. Okay, nitrogen has 5 valence electrons, oxygen has 6, and I have 3 of them. So this gives me 18 plus 5 gives me 23. Well, first off, if you get an odd number for one of these, that probably means we did something wrong. Well, remember this negative means there's an extra valence electron. So instead of 23, we actually have 24 valence electrons total in this structure. So we'll go from there. Nitrogen as our center and oxygen on the outside. Okay, so that gives us 6 of our 24. That means we have 18 more. So 2, 4, 6, 8, 10, 12, 14, 16, and 18. Okay, so what we end up doing is showing all 24 electrons, and again, nitrogen's not satisfied. So we'll go steal from one of the oxygens. It doesn't matter which one we steal from. It just has to be from one of them, and we'll draw our double bond. So that gives us 8 around nitrogen, 8 around oxygen, 8 around oxygen, and 8 around oxygen. And what we're supposed to do is draw brackets around this guy with its -1 charge off to the side. So this would be our proper Lewis dot structure. And again, it doesn't matter which oxygen has a double bond, because this is going to be what we call resonance structure not too long from now. All right, let's look at a couple exceptions of the rule real quick, and I will let you guys off on your own to figure this out. Let's say we have SCl4, sulfur tetrachloride. Well, sulfur has 6 valence electrons. Chlorine has 7, and we have 4 of them. So what that gives us is 28 electrons from chlorine plus 6 from sulfur, so a total of 34 electrons to have to show in this one. So again, sulfur's our central atom because it's the first and the farthest to the left. So we draw our 4 chlorines around it. Okay, so that gives us 8 of the 34, which means we have a total of 26 left. So 2, 4, 6, 8, 10, 12. See, sorry, there's one of the dots that looks like a line, but it looks like a dot, but it actually is not. So that's 12, 14, 16, 18, 20, 22, and 24. Now remember, we have 26 left, so I have 2 more. Well, chlorine is satisfied. So what I'm going to do is I'm going to throw those 2 in on the central atom on any of the sides. So now what I have is sulfur actually having 2, 4, 6, 8, 10 in here. And be careful, these are not in a bond. They're actually on the sulfur. So sulfur has 5 areas of electrons. 1 of a single bond, 1 unpaired, single bond, and single bond. Okay? Let's look at another exception. Let's say we have XeF4, xenon tetrafluoride. Xenon has 8 valence electrons. Fluorine again has 7, and we have 4 of them. So that gives us 28 and 8, so a total of 36. Okay, xenon's our central atom. In this case, it's not the farthest to the left, but it is the first element in the compound, so that's what we end up using. We draw our fluorines around it, and we use 8 of the 36, which means we have 28 more to go. So 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, and 24, which means we still have 4 more to show. So again, what we do is we put those 4 in pairs around the central atom. I'm not putting them next to a bond because they're not part of the bond. It basically means we have 6 areas around xenon. 1, 2, 3, 4, 5, 6. Okay guys, that's about it for Lewis dot structures. What you have coming to you is a practice worksheet. Take your time on it, see what you can do. We will go over this tomorrow if we need more help on it. That's not a problem. We can put Vesper practice off until Monday. If we need to. Hopefully we don't need to though. The answer key will be up front for you to check your answers, and hopefully we will be able to do Vesper on Friday. Have a good one guys, and good luck.